We're going to wrap up our focus on music and audio with the topic of compression. Now, I have to say that actually in music and audio, there's two definitions of compression. There's actually what we'd call dynamic compression, about making sound levels um, more even so that the quiet sounds aren't too quiet and the loud sounds aren't too loud. That's not what I'm going to be talking about. I'm going to be talking about data compression, or how do we squeeze more music into the same amount of data space. So um, we've talked a little bit about bit rate and just how the math works out on that. That the bit rate comes down to for audio or any kind of media is your sampling rate. How often are you measuring the signal, right? The bit depth, the number of bits you're using per measurement. And then if you have multiple channels, let's say with audio, there's left and right stereo. So then you multiply that by the number of channels. So as we've looked at before, for CD quality audio, that's sampled at 44.1 kilohertz per second, 16 bits per sample, and there are two channels. And that works out to about 1.4 megabits per second. So on a physical CD, right, how much storage space does that take? That comes out to around, if you have, want 70 minutes of audio, right, about, a little more than an hour, and that's 4,000 plus seconds there. That works out to about 740 megabytes. And this was the standard. You could fit about 740 megabytes on a CD-ROM. So CDs are designed for album length content, right? A full album's worth, so lots of songs, maybe 10, 15 songs, or things like a symphony, a symphonic work, right? In fact, one of the targets when they were defining the CD spec was, can we fit a performance of Beethoven's Ninth Symphony, which is a little over an hour, onto a single CD? And yes, they made sure to make that happen. So, but what about, I mean, we listen mostly to individual songs. So let's put this in terms of songs, right? So how much storage space, how much data would be required for a 4-minute song, right? Off of a CD, that's 37.9, almost 40 megabytes, so about 10 megabytes per minute, right? And that's at full CD quality. We could reduce the sampling rate, right? So we could take that down, let's say by half, from 44 kilohertz to 22 kilohertz, and then cut down the number of samples by half. So the amount of data we need is one half of that. And of course, there will be some trade-offs in quality due to the reduced sampling rate. We could reduce both sampling rate and bit depth. So let's take that down to 16 kilohertz and 12 bits per sample, and that gives you about 10 megabytes for a 4-minute song. And we could go all the way down to 11 kilohertz, so reducing the sampling rate by a factor of 4, having the bit depth to 8 bits, and now we're under 5 megabytes per 4-minute song, but at a significant reduction in quality, I think you'd agree. So in the modern world, right, which I'll say has started with the introduction of the iPod, which was quite some time ago. But when the iPod was introduced and other MP3 players, there was the promise of not just an hour of audio to take with you, but 1,000 songs in your pocket, right? 1,000 songs. Well, the first media players, right, the good media players like the iPod, had about 4 gigabytes of storage, right, total, right? And so if you're going to fit 1,000 songs, right, now you're talking about trying to get that down to 4 megabytes per song, right? Which is a lot less than we're talking about, especially for the higher quality rates on this table. So how do we get there? How do we get there? In terms of bit rate, right? If you think about it, not just in terms of total size, but in terms of bit rate, right? CD quality audio, we've talked about, is 1.4 megabits per second, or 1,400, a little more than 1,400 kilobits per second. We have higher sampling rates and higher bit depths, right? We're now getting into the 4 to 5 megabit per second range. And then, of course, lower and lower sampling rates and bit depths, we can get down into the hundreds of kilobits or even less than 100 kilobits per second, right? Which may sound more familiar to you because that is the rate that you need to get to around 4 megabytes per song, right? But this isn't how it actually happens. So the goal of compression is to represent the digital data just to make it smaller, though. To try to preserve as much as we can, hopefully all of it, but to make that file size smaller. So this is usually two steps to this, right? There's something we call the coder or the encoder, right, which is going to take the original audio data and somehow shrink it down, reduce its size. And then there's the decoder, obviously, where we're going to take that smaller file, expand it to the original format so that we can listen to it or watch it or whatever it is. So this combination, coder, decoder, is what we call a codec. A codec. Right? It's both a coding scheme and a decoding scheme. Now, there are many different types of codecs, and this is where we start to get into the alphabet soup that you might be, or the more modern alphabet soup that you might be familiar with, certainly MP3 or AAC, which stands for Advanced Audio Coding. Ogg Vorbis, right? That's an open source lossy compression method. FLAC, we've talked about FLAC briefly in class. That's the free lossless audio codec, another open source where it's lossless, right? There's no loss of information. Apple also has a lossless coding standard, right? So I've been talking about them together, but really there are two distinct categories: what we call lossless compression methods and lossy, right? And obviously lossless, there's guarantees, right? That whatever you do, you're going to be able to return to the exact original data, the exact original samples, the full fidelity of the original audio. Right? Lossy, right? We're not going to make that guarantee. We're going to try to make it sound as close to the original as possible, but from a data standpoint, we're actually going to remove or throw out some of that original data. You're not going to get back to the exact same signal that you started with. Okay, so the first case is the easier case. Let's talk about that. Lossless compression is that we're using tricks from data science and information theory to just find different ways to represent the same information, just taking up less space. One of the easiest ways to do that is the methods that we use for zip compression, right? So on your computer, you can take a file, maybe put it through zip, make it smaller, maybe sometimes significantly smaller. And what it's looking for is redundant information, repeated information in that same file. So one of the easiest ways to think about it is that if you have a picture, right, and every row on the picture is the same, every pixel on the same row is the same. Let's say it's all black, a black line. Well, rather than trying to say, oh, I have a black dot here, a black dot here, a black dot here, I'd be saying, I have a whole row of black dots, right? And there are efficient ways to represent that, and that's what we use in fax machines. Used to use simple schemes like that. So zip works this way, and typically you can get some data savings, right? So we can go from something that's maybe 1.4 megabits per second to around 1.2 megabits per second. I mean, if you're really lucky, you might get down to something around half the size. By the way, zipping a zip doesn't work. You can't just take a zip and make it smaller and take it that and zip it again, make it smaller, make it smaller. That doesn't work, right? We need to preserve all the information there. There are limits to how far you can take these sorts of tricks about squeezing out redundancy. Okay? So your best hope with a lossless compression algorithm for audio is about half the original file size, and maybe a little more than half, right? So Apple lossless can get you down to around 600 kilobits. Again, it's going to vary depending on the audio content. All right, so that's good. And this day and age, that doesn't seem like that's that high a bit rate. So you might think, well, okay, why don't we just do that? Well, of course, almost 20 years ago, when MP3 was becoming popular, we could not support those bit rates, and we were trying to get much smaller than that. So that's why we turned to lossy compression methods. Now, lossy compression, like I said, we're going to actually lose some of the data. We're going to make that trade-off. How do we decide, though? What are we going to throw out? Well, obviously, we want to make the sound quality as high as possible, as close to the original as possible. So we want to find the parts that are in that audio that we can't hear, in that original sound file or the original signal that we can't hear. Right? And then ultimately, we're going to have to make some trade-offs between the quality of our audio and the ultimate bit rate or the size of the file as well. So how do we decide what we can't hear? Well, that really is the crux of audio compression or lossy audio compression. So lossy bit rates, right, are much lower than lossless, right? Even if we half the sort of lossless rate, where we're getting over 600 for lossless compression, a 320 kilobit per second MP3 file is almost indistinguishable from the original audio file. And again, it depends exactly how you're recording it or how you're encoding it. But modern codecs can do a really good job at 320 kilobits per second or 256 kilobits per second. Even 192 or as low as 128 kilobits per second. When MP3 was getting big in the days of Napster, most of the content was encoded around 128 kilobits per second, right? And now you're down to about a megabyte per minute, right? And that was sort of the magic threshold for computers and devices of the time, where it was good enough sound quality, pretty good, not quite CD quality, but pretty darn close, and a relatively low bit rate. We're talking about a compression ratio of 10 to 1, right? The MP3 bit rate is 1/10 of the uncompressed bit rate, and that's huge. That's big. You're saying that I can take this file, squeeze it down to 1/10 of the size, and still have it sound really good, right? Or certainly acceptable. So that sounds like magic, right? MP3 can go even lower, by the way. You can go down to 96 or 64, and we've done this for our class experiments, even down to 32, right? And of course, you start making more and more trade-offs, and I think you'll agree that you start really impacting the quality, the sound quality of the audio at that point, once you get below 128 kilobits per second. All right, well, let's return to this question then. How do we decide what to throw out? What are the parts of the sound that we cannot hear? Right. So that goes back to now what we know about human hearing. Right? We've already talked about that. We hear a range of frequencies, and we have the dynamic range between the quietest sounds and the loudest sounds can be huge. That our CDs are already capturing, a large part of this range. But as I pointed out before, there are these regions in the corners that are captured on a CD that we can't hear, right? The information is there, the space is there to capture that, but those are parts we will never hear, right? So maybe there's something there, but of course it goes even farther beyond that. And to get into those details, we need to then understand a little bit more about the human ear, or really our auditory system, how we hear and how we process sound. So here's a little sketch of what I'm talking about. There's, of course, the ears, the thing we see on the outside, right, which don't actually do much, right? I'm sure you've heard of people who've lost their ears, but obviously they can still hear just fine. I mean, there's some small changes, but really what's happening in your ear or your hearing is happening in what we would call the inner ear, right? Or the middle ear and the inner ear. Once you go down the ear canal through the eardrum, and this sort of funny, tiny shell-shaped thing called the cochlea, right? That's where most of the magic happens, right? So the ear, just like a microphone, is a transducer. We're going to convert energy from sound pressure to eventually electrical impulses that are then processed by your brain. So that conversion happens in the middle ear and the inner ear in particular. And it turns out that process of transducing introduces some interesting effects, right? There's a lot of detail in here. I'm going to skip over a lot of the nuances, but just to kind of give you the highlights. The first is that our ears don't respond to frequencies all the same, right? We kind of saw that from the previous figure where I showed the range of frequencies and the dynamic range across frequencies. But there's a famous experiment done by researchers Fletcher and Munson at Bell Labs, just in New Jersey, so not too far from here, where they said, well, what we want to do is we're going to hold we're going to use sine waves. We're going to use individual frequencies and try to see how do people respond to those different frequencies. And they did this for lots of people. And there's a famous experiment that's been then replicated and refined by many others. But the punchline of this was that we don't hear the same amplitude as the same loudness at different frequencies. Right? And what they created were what are now called the equal loudness contours. Basically, what amplitude do I need to maintain the perception of equal loudness? So you can see here for really quiet sounds, right, that's a pretty big range that they need to, that even the quietest sounds that we can perceive around 1 kilohertz here are much, much lower in intensity. And we're talking about a huge range to the lowest sounds that we perceive at the same volume or the same loudness at low frequencies there. And then it varies from low to high frequencies, right? So that's strange, right? I mean, our ears are basically very sensitive, much more sensitive kind of in this middle range here than we are at the low and then some of the high frequencies here. So you'll also notice that for SPL, the 0 dB point is not actually the lowest sound that we can, or the least amount of sound that we can hear. 0 dB is set up to be basically the least amount of energy sound that we can hear at 1 kilohertz, 1000 hertz, that point there. So I've drawn that line across the screen, but you can see that we're actually can perceive some even less intense sounds, lower energy sounds between 2 and 5000 hertz as well. Okay. But if we want to maintain equal loudness across all, or perceived equal loudness across all frequencies, right? How would we do that, or what would that look like? Well, this would be equal amplitude, right? I create different sine waves from at different frequencies, but maintain the same amplitude, right? If I want to maintain equal loudness, this is closer to what it needs to look like. And so these are frequencies going up a scale. So I'm going to play the first example for you. So what you probably heard was that some of those sound louder, some of them a lot louder than other ones, but they all had exactly the same amplitude. So if I then try to equalize that for a more consistent loudness, that's the bottom figure, and that's what this sounds like. Okay. So hopefully that sounded a little more consistent, right? It wasn't perfect by any means, but it's a little more consistent. So our ears are funny, right? Really our auditory system is funny, that we're weighting certain things over others. Gets even funnier, that there's a phenomenon we call masking, right? And this is pretty straightforward, actually. That's the sense that louder sounds will dominate over quieter sounds. So if there's a loud sound happening close to you, you are probably not going to hear a much quieter thing happening in the distance, right? So there's a definition, or a couple definitions here, right? The process by which the threshold of audibility, your ability to hear a sound, is raised by the presence of another sound, right? These are actual definitions from the American Standard, well, the second one's from the American Standards Association. The amount by which the threshold of audibility is raised by another masking sound. So, and again, oftentimes we measure this, or we express this in decibels, right? So that kind of makes sense, right? Loud sounds are going to dominate quieter sounds. Well, let's put these two things together, right? On the one hand, we have a lot of frequency variability, right? Some frequencies are going to sound louder than others. And then we have this idea of masking, that's loud sounds will dominate over quieter sounds. Well, it turns out that that masking is also frequency specific, right? So we know our ears don't treat all the frequencies the same, right? In fact, there's a tendency in our hearing that our ability to tell frequencies apart or tell about differences or changes in frequency uh, is really good at lower frequencies and then gets a lot worse at higher frequencies. So in the low ranges, right, around 100 hertz, we can tell the difference when a frequency changes just a little bit, right, a hertz or less. Whereas if you get up into the thousands of hertz in frequency, a difference of plus or minus 1 hertz, we can't tell that, right? You need to start varying by like 10 or even more hertz for us to hear that. So our resolution is frequency dependent. It turns out that masking is also frequency dependent, right? And the way that works is that if you have a particularly loud tone or frequency, right, that will dominate over nearby frequencies of lesser intensity or lesser loudness as well. Right? So now this is really the key to MP3 and then the crux of the idea, the big idea here, which is that if we can figure out, hey, these louder tones, these louder frequencies are going to dominate over quieter ones, right? That gives us a great way then to determine what we're going to hear and other things that we're not going to hear. And if they're still there, we can throw them out and then reduce the amount of data that we need to capture the music or the sound. Right? So that's a lot. This is a big idea, and there's a lot packed in there. So what does it take? How do we actually do this? Right? So the guiding question here is, how much amplitude does it take for something to mask something else? Right? And obviously, if it were a big sound, a big nearby, if you're standing near a jet engine, you're not going to hear anything else. But like I just said, things can be very localized in terms of frequency. So even within music or within things that we would listen to, we can look at individual frequencies. So we actually did this experiment as part of class. I gave you each a different set of masking tones. So you always had a 5 kilohertz tone, but then we varied other tones around that to see if your listeners heard any difference, right? If they heard any difference from just the 5 kilohertz tone, we'd say that then they heard it, right? Then they think it's there, right? But if it sounds exactly the same, if there's a 5 kilohertz tone here and another one next to it, like let's say a 4700 hertz, but it's lower in amplitude, and they say, oh, that sounds exactly the same as just the 5 kilohertz. Well, they didn't hear this, right? So that is how we do this. That's how we do the experiment, to figure out, like, what are these masking thresholds, right? When can we start to eliminate sounds? So let me show you what that looks like. So this is a spectrum, or a short-term snapshot just of audio, and let's say there are these frequencies in this little slice of music or audio, right? So let's find out what's the biggest one. Well, that one's there, right? That's the tallest one. And then we're going to look at a range right around that. We're going to use these masking thresholds that we've then, the masking thresholds are determined by data, by experiments that we've conducted on listening experiments with people to determine, well, most people don't hear it when it's under this line, right? So here I'm just depicting it as a triangle, but it's a little more complicated than that. But it's basically like this. There's sort of a tent that forms around, a particular frequency. So we can see, well, that's the peak here, and here's the threshold, and oh look, this one falls beneath that. This one is above it, so we're not going to touch that one, but this one falls beneath it. So let's just get rid of that one, right? And then we'll move on to the next biggest peak, which is that one there. Do the same thing. Now the masking thresholds start to get wider and wider as we get higher in frequency. So this triangle is a little bit wider. And again, we find a tone here, or a frequency that is beneath the masking threshold. So let's get rid of that one. And there's our next highest one. do the same thing. Now this triangle is very narrow because it's low frequency, or this masking threshold is low, is narrow. So nothing to get rid of there. Let's move on to the next one. Oh, this one, high frequency. So, oh boy, that one's pretty wide. And now we have a lot of other things that fall beneath that threshold. So we can get rid of those. Like that. And I think we'll do one or two more. This one's at a low frequency. It's gonna be narrow, but still there's something we can get rid of there. And maybe one more, right? Right, this is at a higher frequency, and I've just gone in order, right? What are the biggest, the frequencies of highest amplitude, the highest weight, right? And so again, we have one there that we can eliminate. So I've just gotten rid of a lot of different frequencies. And again, since Fourier says that, you know, any signal can be composed of those frequencies, right? I decompose it into those frequencies, I get rid of a bunch of them, and this is what I'm left with, right? And I can turn this back into sound, right? And just to show you how far we come, this is what we started with, right? The dotted lines were things that we've eliminated. So obviously, MP3 does this on a much more detailed way, right? But is able to then eliminate a lot of frequency content, a lot of data there that you know, if you're reducing to a fact up to about 10% of the original, right? You've thrown out 90%. 90%. That's what our ears really do latch on to. The loud things, the dominant frequencies, right? To that extent that we can throw away, you know, up to 90% of the sound and still hear something that's really close to the original, right? So from there to there, again, I threw out about half of them, but MP3 does a lot more. And then the final piece is just the figure I showed before, where that, you know, there's certain areas of frequency that we're just not going to hear. We're not going to hear. So things below the this line, which is the threshold of audibility, right? The 0 dB SPL equal loudness contour, all this stuff down here, we are just not going to hear, right? So when we're doing this elimination, we also check to see if anything falls below this line here, right? And that also helps reduce the amount of data. So that's the essence of how lossy compression, or sorry, MP3 type lossy compression. What we call this is psychoacoustic compression, because it's based upon not just the acoustics, but the psychology, right? What our brains are doing, how we're processing sound. So this is a theme we will return to as we look at all different forms of media, right? This is not just for audio, but to kind of maintain this distinction between what are the physical quantities that we can observe and measure, right? Put a number against, and then our perceptions of those things, right? So the physical quantities are things like amplitude, frequency, power. Those are things we can take our waves, do measurements, plug them into an equation. We can get solid numbers on these things. But just as important, whether we're dealing with sound or we'll see later on in vision and even touch, are our perceptions of that. You know, we often call these things, we've put names on these things like pitch and loudness and timbre. And we've even tried to assign, you know, some numbers to these things, but they're not numbers you can directly measure from the sound or the music or the signal, right? So it's always important to maintain this distinction, right? And then this field of psychometrics, and specifically in sound, it's psychoacoustics, is about this relationship between the physical things that we can measure in a signal and the way we perceive those things. The sounds we hear, the loudness, or in vision, it's the colors we see, the textures, you know, our sensitivity to light, those sorts of things, exposure, contrast, and those things. So I will end this lecture here because this is kind of the jumping off point for the rest of our content. I think this will be useful in doing your analysis for part 2 of the project, and I look forward to talking about this more with you in class. Thanks.